And you can go mad with some chicken wire if you want something nice and big with a corner reflector. You don't have to necessarily have one that size, but that's somebody going bonkers. On the other hand, if you've got an old parasol at home, no. So somebody trying to get their 3-meter dish the cheap way. And that's my baby. So that's actually, which I'd recommend these, but they're rare as hen's teeth, as Tarmac and Triffid Band 3. It's made a 4x4 dipole array there. So that covers the 1420. Works really well, corner reflector design. But again, I've never seen them anywhere else. Difficult to recommend it when you can't get hold of it. But if you know any spare going around, I would like a second one. But they are, so that's 86 by 86 centimeters. But just to say, you don't need that. It performs about the same level as a 1-meter dish, which is basically anything 1 meter in size, essentially, is what that's performing as. It's got one great advantage when I put it up. My wife was okay with the look of it, so that's quite important. So I said about how to actually use it. The software, you just, as I say, it does a drift scan. So you just aim it pretty much any direction. Give generally go for south. Somebody's had enough. And the software just follows over 24 hours. So, but then you change the elevation every day or two. So this is the rather complicated or rather uncomplicated mount I made for it. There's just wooden thing here, and you probably notice at the back there's a couple of wooden struts with, I think another picture there. Well, yeah, you can see them now with some holes in, so I can just change the elevation. We don't want anything complicated here, Oh, that's just another alternative. A friend of mine, Alex Pettit, who's the aerial guru for SARA, sent this out to me from the States. That's his latest creation. It's a plate Yagi there. And then there's this little baby, which I picked up for £50 off eBay. These are sold as solar cookers. So you can pick up in the States. They're not so readily available in the UK. You can get them off the American eBay site. You just pay about another £50 to get them delivered, or you can get them off AliExpress. Again, I was having a chat with somebody earlier on about this, and they were saying, well, how well are they made? We had a big chat about this on SARA, and we've ended up with this conclusion, which was it doesn't matter whether there's a 1 to 2 centimetre variation across the wave surface, because you're talking about 21 centimetres. So even if you had 2 centimetres variation of the wave surface, that's still 10th Lambda in terms of the wavelength. So it's still pretty good. Okay, if you're going for 10 gigahertz, that would be problematic, but we're not. So the only real question is you're trying to make it some way of mounting it, and then a waveguide. Just say my wife was not so happy when she saw that had turned up. So there we are. So at the moment, that cantenna I created is being brought back into service, but this time facing in the opposite direction, now down onto the dish to act as a waveguide this time. Obviously not particularly well mounted there. It's just to get started and try it out. Okay. Everybody tends to ask me about beam width on these things, so just in case you're interested, I thought did some beam width calculations. So I don't know how many decibels you're interested in, but let's say if we took 3 decibels, then we got 14 degrees on a 1 meter dish, and down to 9.5 degrees on a 1.5 meter dish. And if you were lucky enough to have a 3 meter dish, you'd be down to 4.75 degrees. So you can see the difference that it makes. But in terms of the actual question of mapping the Milky Way, it really doesn't matter. And that's what I want to prove to you in a minute or two. Like lots of these things, you can address the question and say, how good can I get? You can ask that question and try and navel gaze. It's a hobby. You can do what you want. There's nothing wrong with that. If you want to try and get the best aerial that you can, and you want to try and get the best kit and the most accurate mapping exercise you can, wonderful. But if you want to demonstrate the arms of the Milky Way, if you want to see, want to weigh the Milky Way, if you want to pick up dark matter, then you don't need all that detail. And the 1 meter or even anything much smaller will do the trick for you to some extent, more than some extent. So I mentioned it. That's the new, Sorbird, the new one I mentioned to you. It's somewhat smaller than that, by the way. And there's just an example of a dongle. I use one as RTL SDR blogs, not that it matters too much. When it comes to computing power, I went along to that rather fantastic Arduino workshop yesterday. That was quite marvelous. And a lot of amateur radio astronomers are using that sort of small machine for actually monitoring their computers. But that does somewhat involve having to program those computers to do it, whereas I understand Windows and they do the simple bits. So I picked up these little mini PCs, which you get them off eBay for £85 each, and you get 8 gigabytes of RAM and 256 gigabyte SSD and an i5 processor, and it does the trick very well. So I have what's called my stack there, which is a little part of the little things. I have one running each of my radio astronomy experiments. But as I say, a lot of people just use the Pis and the Arduinos. The other problem I had when I stuck it outside, so I get this box and stuck it all in. In this particular case, it's an old laptop that somebody had given me. As I say, any old thing works. So I stuck it in this box underneath the aerial the first night. When the Dex data look at it, and there's this pool of water in the bottom, which is dew that's just precipitated on the inside of the box and collected at the bottom. So the white box at the top is those little 60-pound caravan dehumidifiers that you get off Amazon. I guess that produces more RFI. So I mean, I have tried coating the whole lot in silver foil, but honestly, it maps the Milky Way even without bothering. Right, one thing I did come across out of interest is some of the software runs into problems with Windows updates. There's a neat little program called Windows Update Locker, which is fantastic. Just hit. Okay, right. So software. Okay, so how are we doing on time? Just 3 minutes past. Okay, just for what it's worth, this is actually the hydrogen signal being collected here. Okay, so there's a couple of options. So the Gyroscope in the Box project recommends SDR sharp. I don't know if do you tend to use that regularly? So they've got something called the IF average plugin. I don't know if that I assume that probably isn't used for what you're doing, but that allows you to collect data over a period of time and essentially stack it all together. Very, very, very neat. So that's definitely one way of doing it. Works very well, the one that they recommend. The other major alternative, I think, if I go on this page, is this one, which is the one that I'm just a massive fan of, which is my friend Ted's piece of software called Easy Radio Astronomy, which is a series of Python scripts with a collection program and a set of analysis programs, which basically does all the analysis for you. Just press a button and goes bang, 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 and 250 plots come out at the bottom. Literally, including mapping the Milky Way for you, demonstrating dark matter for you, weighing the Milky Way for you, and piles of others. And the issue becomes trying to understand what all these plots are about. But he's quite helpful, is old Ted. So that's what I recommend. It really requires very little understanding to use, and probably quite a lot of understanding to try and work out what's going on at the end of it. But and you don't need to understand Python, you just need to be able to run the scripts, that's all. And it's all available on GitHub just to download. So here's an example, there we are. So that's the collection program. It's worth saying that Easy Radio Astronomy will actually process the data from SDR sharp. So you can use the two together. So again, that's Easy Radio Astronomy's collection program there. the hydrogen signal there being detected. And it shows a couple of things about it. So we're on, for some reason, we're slightly off on here on its major thing. So 1420.05 basically for the main signal, but you can see there's some breadth to that signal. So that's the Doppler shift that's around the central signal. And within that is all the data that tells you about the other arms, the Milky Way, etc. On the right-hand side, you will notice that there's a blue zigzag line here. Anything to do with radio astronomy, calibration is very important because you're dealing with very weak signals. So in this particular case, the program's using a rather neat way of calibration. You can stick a 50 ohm, I think I've got a picture in a second, a 50 ohm dummy load on, quite effective. But one of the big problems that happens is that as the night goes on, the temperature of the whole rig changes, and that tends to affect your signal collection as well. In this particular case, what the program's doing is it's not bothering with the dummy load. I mean, probably the best way of doing things is to have the dummy load with an ability to switch it in and out and do that on a regular basis. Here, though, it's doing a sort of proxy for that, which is every other sample, it's switching the signal from 1420 to 1423. So you don't pick up hydrogen at 1423. And so that gives you that offset allows you to pick up essentially the same signal without the hydrogen and use that for calibration. And that tells you, there's EZ colinteg quality there. That's the number of samples that are being integrated. So there's 31,000 samples are being basically stacked together each time. And then you've got obviously the azimuth and the elevation, tell you what we're pointing at the moment. Okay, again, that's just to show you the Doppler shift. And I mentioned about it, that's just a dummy load on there. And that's, as I say, just the 3 megahertz offset. Okay, so this is what I'm sure you're quite interested in the results. So before we get to the map, so this just shows you the data being collated on a single chart. So the background on this chart is professional data. And it shows the Milky Way at a particular projection. And the green dots are my data being collected. So each line is a different elevation. And you can see there that it peaks up each time it goes across the Milky Way. And that's putting it all together. So it's now starting to produce a map on there. And you can start to see, so there's some limitations to the way this is collected, both in terms of where we are and some difficulty in collecting data from certain parts of the Milky Way, but probably more important, something to do with the mathematics that underpin this, which limits the quadrants that you can get to. So we're mostly limited to our one particular quadrant between sort of 90 and 0 degrees there, and a bit down the second quadrant down here. But on the right-hand side, you can't really get any data out of that. But you can see here that you've got one arm, and if you look here, one very bright arm, and if you look behind it, you've got another arm that's coming out behind it. What blows my mind is that arm is behind that arm. So if you were looking out with a camera or a telescope, you wouldn't be able to see that. And here I've sort of just downloaded a picture off Wikipedia, a sort of a commons picture of the Milky Way, just overlaid it so that you can start to get an idea of where these arms are. And I've labelled them out for you. So we've got, so the main bright one is Sagittarius. You can see we picked up the Cygnus spur at the bottom, a bit of the Perseus at the bottom. There's actually a tiny bit of the Norma outer arm at the top. And the second arm behind us is the Perseus arm. So for what it's worth, that's over 500,000 observations over 2,000 hours to generate that picture. So it's taken me about a year to get that far. Now, I mentioned before about other things that you could do with it. So again, we've got here showing some of the different velocity measurements at different distances from the centre of the Milky Way. And importantly here, if we're here down where this this sort of icon is here down here, sort of like a rainbow, you can see our line of sight is the black line here, and you can see that depending on what you're looking at, you will see the stuff moving in different directions depending on where you're at. And so from that you can do some calculations. Now this is also something off Wikipedia, just an idea to get for you. So when it comes to, this is about dark matter we're moving on to now. And I want you to look at the two diagrams and see if you can see the difference between the two of them. And the thing you want to notice is that the centre's moving at the same speed, but the outside on this side is moving much slower than it is on the right-hand side. Can you see that? Right, okay. So this is what you'd expect to see. Just do that one more time. On the right-hand side is the one that's meant to demonstrate dark matter, okay? So they often describe the one on the right-hand side as being like a bicycle wheel, where the outside of the bicycle wheel moves at the same speed as the inside. Now, start off, ignore the right-hand side for the moment. If you look at the left-hand diagram here, so this is the left-hand diagram is not my diagram. So this is, again, off Wikipedia. And this shows, it's a graph that shows the distance away from the center of our solar system and the velocity around the sun, and it's the planets. And you can see here that planets that are closer to the sun, such as Mercury, Venus, and Earth, are going much faster than planets that are far away, such as Uranus, Neptune, and if you want to call it a planet, Pluto, out there. And so that's called Keplerian rotation, because Kepler, with his rules, described that relationship. And so that's the graph that was on the left-hand side that showed things moving much slower on the outside. If you look at my graph, this is my data here on the right-hand side, just to point out that for various limitations of the experiment, I can't get much closer than 4 kiloparsecs to the center of our galaxy, and you go out to about 8 kiloparsecs, which is the distance of the sun away from the center of the Milky Way. And you can see there that graph is absolutely not what the graph is on the left-hand side. In fact, the graph on the right is probably much approximates a straight line, which is, okay, take with mine from my backyard, which amazes me. So that is the smoking gun for dark matter. The fact that something has to explain why that is not dropping in velocity as it goes further away. Now, I know I've run out of time, so very briefly, what have I got? Just that, yeah. That's just to throw in to say I just weighed the Milky Way while I was about it at the same time. That seems to work very, very rigidly, very well. You can see a nice straight line from center. And let's show you some different types of aerial. Just forget that. Okay, and there we are. We're just finished with that. So do feel free to contact me if I can help you in any way and you want to take this further. If you want to read any more, there's my website there. So thank you very much indeed.
We have time for about one question, if anyone's got a burning question in the room. Right here.
Just the elevation of the antenna. Sorry, yeah. I'm John, G4NEY. Just interested, the elevation of the antenna you were showing with your wonderful mechanism. Were you just moving that over the period you were recording then, or?
Yeah, so when my original mapping exercise, you only need 24-hour drift scan is what you need. So I did it for 2 days, to make sure I got a full 24 hours, and then shifted it. I mean, now I'm repeating the exercise with a week in between, just to try and see if I can get pull out a better signal-to-noise ratio, so I can get a bit more brightness or be able to distinguish more of that outer arm But yeah, you just really need 24 hours on it.
Thank you very much. At that point, we're going to draw a line under that, ladies and gentlemen. Thanks very much to Dr. Andrew Thornett for a wonderful talk this morning. If you have any further questions, do come up and talk to him after. Thank you very much.